Hi, welcome to this video. In this video, we'll be discussing about short-time Fourier transforms. Okay, so the need. So signals are changing with time, and spectrum does not inform much in that case when the signals change with time. For example, consider this signal. It is changing with time. So the frequency is high here, then the frequency is low here, again it is high, again it is in some medium range. This is like a frequency modulated signal, an FM signal, and this one is a constant signal, right? If I plot the spectrum x e to the power j omega, the magnitude plot will look something like this from 0 to 2 pi. It is a real signal, so you see this is symmetric, right? It's an even function or a conjugate symmetric function. But what we can notice here very clearly is that when this is a constant sinusoid, or let's say constant frequency cosine signal, there you get a high peak, but because of this changing frequencies, there is a lot of smearing, and you don't know exactly what is happening in the signal, right? So the spectrum does not inform much. What do we do? And okay, is this a real problem? Yes, this is a real problem. Signals do change with time. Consider audio signals. Let's say if I'm playing flute, I'll play different notes at different times. If I'm playing another instrument called cello, I'll play different notes, bass, horn, oboe. So all these, when I'm basically any audio signal, it's changing with time. And similarly, the same is true for any communication signal, video signal, things like that. They change with time. So how do I deal with them? Okay, so this is a strategy which people invented to deal with changing signals. Why do you want to analyze the entire signal in one go? Why can't you take small windows and such that each window has constant characteristics? Let us consider an audio recording. So the whole audio recording is changing with time, but if I take a very small window here, let's say a 1 second window, then what I find here is signal looks pretty much constant, right? I mean, constant in the sense that the frequency or the frequency characteristics are almost constant. And then, okay, and if I do a Fourier analysis of this window, means this is the waveform, and if I plot the spectrum, which means the mod of x e to the power j omega, then it will look something like this, right? Okay, it means this is only from 0 to pi or less than pi. That's why you don't see the symmetry here, but it is a spectrum. Okay, and why I'm plotting it in this fashion? So you'll see the reason in a moment. I insert back this slice into here so that the frequency, so the frequency is here. This is your f in hertz, let us say. And this is the magnitude. And if I insert this slice here so that the magnitude now is in the third dimension, basically the intensity specifies your magnitude, right? So the peak here, it becomes dark, and the lesser peaks become lighter, right? So you can see the three-dimensional structure, which is plotted as an intensity plot. Frequency is here, and this time corresponds to this time. Basically, this window corresponds to this spectrum at this small time interval. Okay, I think this makes sense. This picture conveys a lot, so go through it carefully later. Okay, and if I plot the spectrograms of individual instruments which we just saw in the previous slides, like the flute, so it will be like this. Cello, you can see clearly how the frequencies are changing with time, what notes I am playing with time. Bass, horn, oboe, so all these changing signals. Now with the help of Stft, I can get very clear idea of what exactly is happening in the signal. Means, okay, not everything about the signal, but yes, at least the things which I am interested in mostly. Okay. Another now challenge. Okay, if I mix the signals, the waveforms look very gibberish. Like I cannot make out what is happening actually. But if I plot the spectrogram, then see, you can still see much of the structure. These horn lines are visible. This flute is visible. So still it is quite distinct, and you can do much more with the spectrogram as compared to the original waveform. Okay, so with this we come to the general theory, spectral analysis, analyzing the frequency contents of a signal, and this is called STFT, a short time Fourier transform. This is a time-dependent Fourier analysis technique. As I just now had shown you in the previous slide, how you take small windows and each window in time is analyzed with the Fourier analysis, right? So let's go into some mathematical details of STFT. Okay, so this is the Fourier transform. So you have seen previously x of n e to the power minus j omega n. But now we take small windows, time-dependent windows. Let's say Wn is a time-dependent window. It is one for only very short duration, and it is 0 mostly. Right? This window will put a constraint on how much of the signal I want to analyze. Okay, and let's say my W is simply let's say a rectangular window from 0 to some r minus 1, 0 everywhere else, right? Then this makes much sense. Now it looks like a convolution operation, right? Convolution of xn with, or xm with wm e to the power minus j omega m. Okay, so now if my w is a window of length r, window length is r as I have plotted here, then my the formula, because it becomes like this, because my n does not go from minus infinity to plus infinity, but only from 0 to r minus 1, because otherwise wn is 0. Okay, so this is the DTFT, discrete time Fourier transform. Now if I want to plot the discrete Fourier transform, I just sample it at omega k's, where omega k is 2 pi k upon capital N, where n is my a number which I have chosen. It's the endpoint Fourier transform. Right? How fine spectrum do I want? Okay, this is my xk comma m. The same thing, just computed at discrete omega values. Let us analyze it more pictorially. Let us say my x is a signal. It could be of potentially infinite length, no problem. So look at this now. My x of m minus n. So if I choose some value of m, let us say this is my value of m, and my n is varying from, let's say, 0 to r minus 1, 0 to 1, 2, 3, 4, 5, 6, 7. So in this case, r is 8, right? In the example here, r is equal to 8. So my x of m minus n will be changing like this. And on the other hand, I have w of n. So as my n is increasing from 0 to 7, my w is changing like this. Let us say this is my window w. And if I am multiplying, this will get multiplied with this. This will get multiplied with this. The 3 will get multiplied with the 3, this thing here. And in this way, I will be multiplying x. If w is a rectangular window, or means it's constantly 1 everywhere, then this will be just 1, and I get x of something e to the power minus j omega n. This is like the normal Fourier transform, right? But of a signal x which is time limited. No longer it is infinite in time, or aperiodic in time, right? So this is the basic idea of STFT, that you take a small window of x, analyze it with the help of TFT or DTFT, and then increase m further, let's say by several steps or one step, and then again do the Fourier analysis of that shifted window, right? So let us now analyze the effect of window. So if I change my window length R, what is the effect on the STFT? Let us say my signal is this, which you have seen, the FM part followed by constant frequency sinusoid. Then if I take a window of length, let us say 0.1 second, which means my capital R will be how much? Capital R will be basically T into Fs, if you remember it, my sampling rate. So if my window is 0.1 second window and I analyze this part, then move my window in this way, if I analyze the entire thing, I plot the spectrogram or the STFT, then it looks something like this. So the spectrogram is basically x of k comma m mod. You can square it, but that is all right. Or if you just take magnitude, then it is called a spectrogram. This R square term, right? So this is my K versus M, or basically K is the discrete counterpart of frequency, M is the discrete counterpart of time. And if I plot it in the continuous time domain, it looks something like this, right? Now what happens if I increase my window length? Now let us say if I make my window length double, now it is 0.2 seconds. Then the spectrogram changes like this. If I further increase my window length to 0.5 seconds, spectrogram looks like this. Further increase to 1 second, spectrogram looks like this. Okay, so what is happening as I change my window length? Two things I observe. One is that for this constant part, just focus on this constant part from 1 second to 2 seconds. You see here, the frequency estimate is very rough. It becomes sharper, sharper, and sharper. So here, very sharp estimate of your constant frequency. So when your signal is at a constant frequency, you get, by increasing the window length, you get sharper and sharper estimate of your frequency. But when your frequency is changing with time, let's say in the first half of the signal, from 0 to 1 seconds, when the frequency is changing with time, the analysis become more and more smeared across time, smeared over time. Why? Because if you take a longer window, then you are losing the fine information in time, right? Means you are losing fine temporal analysis. The resolution, temporal resolution is spoiled, right? So let's go backwards. So here you see everything is smeared in time. But if I make my window smaller, then you can see things are separated, well separated in time. Further smaller, it is even more separated. Further smaller, you can very precisely see your how your boundary exactly at 1 second, that your signal characteristics are changing from some high frequency to a lower frequency, and very precisely you can mark. But here it's all gibberish. Here it is also smeared. Here it is visible but not as sharp as this. So what we observe finally, as my window length increases, my frequency resolution increases. As you can see, my frequency resolution is increasing as I'm increasing my R, but my temporal resolution is decreasing. Right? My temporal resolution, this one, is decreasing, and it is completely smeared with a very long window. Right? This is the idea which I want you to take home. The effect of window length on STFT. Okay, now let's consider window type. How does my STFT change with what window I choose? If I choose a rectangular window, which means simply it is 1 everywhere in the region of interest and 0 everywhere outside. Right? My region of interest is only, let us say, 100 samples here, 0 to 99. And my spectrogram will look something like this. If I take this kind of a window, my spectrogram looks like this. Why are there these extra structures? Why am I seeing these extra structures? So with a rectangular window, I get these extra structures. There is a reason. Let us analyze that in detail. Why so? Why those extra structures? So basically what is happening, when you multiply in time domain, in the Fourier domain you are convolving two things together. So there is an example. So let us consider this with an example. For example, if my x is a cos 2 pi n upon 25, it is just a sinusoid signal, pure sinusoid, and the n is, let us say, infinite. It goes from minus infinity to plus infinity, no limits on that. And my wn, which is basically my window, it is confined to 100 samples, means the capital R is 100, which means it is non-zero, which is exactly 1 only for 100 samples and 0 everywhere else. So okay, now I want to multiply the two and take the DTFT so that I can take the STFT, right? Now, before we do that, what will be the x e to the power j omega? What will be the Fourier transform for xn? Okay, so let's go back to the basics. X e to the power j omega is xn e to the minus j omega n summed over all n. Now, what is my xn? My xn is simply cos 2 pi n upon 25. So when will you remember that whenever you have very sharp frequency, the time domain, when you have sinusoid signal, the corresponding DTFT is a sharp Dirac delta function, right? So this will be a Dirac delta function, but where will that peak occur? The peak will occur when this omega will match this omega. Basically, when omega is equal to this omega. So which means the peak will occur at omega naught equal to 2 pi by 25, right? And if you solve it, it is 0.2513. So let's plot. So this is my xn, which is potentially infinite. It is infinite signal, and w is a finite signal of length 100. Okay, my x e to the power j omega will look something like this. This is a Dirac delta function, but okay, for plotting I have plotted it as a finite because I have taken a very long. Okay, fine, leave that part. But so this is basically a Dirac delta function. So what is this frequency? You know, 0.2513, 2 pi by 25, right? Now, how does my W look like? Capital W means the Fourier transform of this window. The Fourier transform of this window will be a sinc function. Basically, it has the central lobe and then side lobes. So if I multiply the two together now, in the time domain, my yn will look something like this, right? I have curtailed my xn just in the range 0 to 99. On the other hand, my Fourier transform of this yn will look like this. Why so? Because we have convolved my w of e to the power j omega with x e to the power j omega. Since x e to the power j omega was simply a peak or a Dirac delta function, so my convolution is just a shifted sinc function. So this is again, as you remember, 0.2513. And this is how much? 2 pi minus 0.2513. Right? Okay. So what is the problem? Why are there so many side lobes appearing? So these are longer. Okay, these side lobes are appearing because of this. The side lobes are appearing because of very sharp cutoffs at the boundary. Okay, this is the STFT thing, DTFT. Now, if I take a longer window, you remember when you take a longer window, you get very sharp estimates of your frequency. Then you get smaller side lobes and a very sharp central peak. But our constraint is that we cannot take a very long window because our signal is changing with time. So what do we do to reduce the side lobes and make the graph look cleaner? Okay, so basically I change my window type. Instead of taking rectangular window which has very sharp cutoffs, I take a Hanning window or a Han window, which is smooth at the corners. So you compare it with the rectangular window where there was a sharp cutoff at the corners, but here this one has very sharp tapering, a very smooth tapering at the corners. Okay, so let us see what is this window exactly. You have a cosine signal, and this part, basically this is your Hanning window. You just invert it and raise it so that it is between 0 to 1. So the formula is like this. You have inverted it with a negative sign and you have raised it by adding a bias to it. That's it. And if you want to know more about different types of windows, not just Hanning window, go to this link and you can find various popular windows. Okay, now let us analyze. Okay, so now you can see the side lobes have gone and the extra structures have gone away. Basically, when I plotted my Stft in the beginning, I used the Hanning window without even telling you. But then I told you that the window I'm using, if I use a rectangular window, I get extra structures. But with a Hanning window, no extra structures. You get a very clean looking Stft. Okay, let's analyze this window in little more detail. You know your x of e to the power j omega are those Dirac delta functions. And your Wn, the Fourier transform for this Wn, it has very little side lobes. See here, almost no side lobes. So if I do the same analysis, basically if I multiply my x of n with the W of n, so with the rectangular window I was getting these sharp peaks at the corners, but here I am getting very smooth tapering, right? So my y of e to the power j omega will look very smooth. You can notice the side lobes have almost gone. So what you see is a wider central peak. So this peak has become wider as compared to the rectangular window, right? The peak has become wider, but negligible side lobes. The side lobes have gone away. So this is a nice compromise. Okay, we are losing a little bit on the frequency resolution, but we are not getting extra structures which can spoil our analysis. So this is perfectly acceptable. So that's why Hanning window or smooth looking windows like Gaussian window, they are more popular for Stft analysis. For references, you can go through Oppenheim book, chapter number 10, section 2nd and 3rd. And also with this video, I'll be supplying codes which you can run and see the effect of changing different parameters on your Stft analysis. As that code I also used to generate these plots which you saw in this video. Thank you very much.